Welcome to solverfy.
.56, we're thinking about an electron that's being emitted from a nuclide with A equals 150. We don't really care what it is. The kinetic energy of the electron when it leaves is 1 mega electron volt. First, we want to find the de Broglie wavelength, and then the nuclear radius. And then we want to discuss whether this electron could have been confined as a standing wave in a box, a box type potential in this nucleus with the radius it has, and then discuss a little bit what this implies about the what is apparently an argument that had been made at some point in the past that electrons can actually exist in nuclei. So getting started, the mass of an electron times c squared is 0.511 mega electron volts, or 511 kilo electron volts. It's a useful thing to know, and despite my research I've been doing for years and years having nothing to do with atomic physics, I still remember these things. I use them so much in my classes. And then HC, also another thing, is that it's the 1,240 mega electron volt femtometers. Usually in electron volt nanometers, but you just move around the powers of 10 and you get mega electron volts and femtometers. So the de Broglie wavelength is going to be Planck's constant divided by the momentum. It is going to be Hc divided by the kinetic energy squared plus 2 times the kinetic energy times mc squared. And so the wavelength of this electron is going to be 900 femtometers. Now the size of this nucleus, we just use the equation that it goes like the mass number to the 1/3 power. We find that the radius of the nucleus is 6.4 femtometers. Now for parts C and D, so we see here that the wavelength of this electron is way longer than this nuclear radius. And if we were to have, if you have a sort of box potential with a characteristic length L in one dimension, then the largest wavelength you can fit is going to be 2 times that, because if you recall, we have, here's our box. You can fit, the longest wavelength has its half wavelength that fills the box, so lambda over 2 equals L, and then all the other ones obviously have to have shorter wavelengths. So our lambda over r here implies this can't be this can't be confined in the nucleus as a standing wave. It is true that with a finite well, the wavelengths can be slightly bigger because they kind of bleed out into the portion outside of the well and so on, but not a whole lot of a difference there. In this case, we have like 12 femtometers here is like the diameter, is just way less than 900 femtometers. So there's no way you can fit this into a box this size. And so this sort of very strongly implies that electrons don't live in the nucleus.